Alrighty nerds, well today we are going to start learning some of my absolute favorite mathematics. Today we're going to begin learning about logarithms. I love these things. And the reason why I love these things is because it's the first mathematics that I ever came across that beat me. I failed the logarithm chapter when I was in Algebra 2 honors. Failed. F. Okay? And now it wasn't Mr. Bluebaum's fault. It's because there was family issues and I was removed from school for a month and had to go live in a shelter somewhere in another district. And their school was learning material much slower than we were. When I came back, I had missed the entire chapter. Had to try to teach it to myself, went horrifically wrong, failed. I got a degree in mathematics without ever fully deeply understanding what logarithms do and why they work. And I was able to get answers. But it didn't matter that I could say the right things and I was getting right answers. I had no idea why it worked. And it wasn't until I became an Algebra 2 teacher where something finally unlocked for me. And when it did, I remember I just got like goosebumps. I was so freaking thrilled because all of a sudden it was easy. And because I remember why it looked like magic to my students, I know exactly what to not do when I teach it. And I know exactly how to get you to understand how they work. I will need you to play my game. I will need you to answer me as a whole class, and I'll tell you the script here in a minute when we get to it. For right now, nerds, let's talk about operations. In elementary school, the very first operation that we teach you is addition. And you all eventually understand what addition means. The instructions for a plus sign say, take whatever value is over here and whatever value is over here, put them together and see what your new value is. You all basically understood that very, very quickly at a young age because you can do that, on your fingertips. All right, well, soon after addition, you learn how to undo it. Subtraction. You see, these are inverse operations. And later on, when you get to pre-algebra and algebra, you learn to call them inverse operations and know that they cancel each other in either order. The next operation that you were taught in elementary school is multiplication. And you quickly learn that it's just repeated addition. And so you understand its instructions and how that symbol works and what this symbol tells you to do to numbers. Soon after that, you learn how to cancel it with division. Which, by the way, did you guys know that this represents a fraction bar with a numerator and a denominator? That's why it looks like that. Anyway, you're taught how to divide, the inverse of multiplication. And then you learn at some point in time that they cancel each other in either order. Sometime later on, I'm not sure when, you learn how to use, exponents. And then you learn how to cancel said exponents. What I'm getting at here is, throughout your entire math career, you've been taught operations and then their inverses, and then a new operation, and then their inverses. And then we try to tie them all together and show you how they're all related to each other. Like this one's just lots of this one. This one's just lots of that one. You know what I mean? This one is lots of this one, which is lots of that one. So on and so forth. You might not have realized it, but in the last chapter, we did things like this. And this too is an operation. This operation is called the exponential base. This is a power. This is an exponential base. So exponential bases are an operation, which means they can be canceled. So the essential question of of the lesson is, well, now that I've said it, what is a logarithm, but we'll get to in a second, is how do we solve for unknown exponents algebraically? Look, I tell you 2 to the x is 4, and you would tell me what? What is x? 2, right? But, okay, yeah, so we all know x is 2. Yay! But my question is, how did you know that? What math did you do? What algebra did you do? Now, you may have said this. You may have said, well, I know it's 2 because 4 is a number that can be written as base 2. And since the bases match, I could just say the answer's 2. But where did those bases go? You can't just say, don't worry about them. That's not math. That's magic. I mean, if I told you that, x plus 1 was 5, you would all know that the answer is 4. But you wouldn't say the answer is 4 because I just know it's 4. There's an operation that you could perform that gets rid of the thing that's in the way. And that's how you know the answer is 4. So how did you know the answer was 2? Same thing's happening over here. You see 2 to the x equals 8. I know that we can all see that the answer is 3. I'm aware of that. And the reason that you would have said that you know the answer is 3 is because, well, 8 is 2 to the third. And the only way these two things are equal is if the exponents are equal, therefore x must be 3. And they go, great, but what algebra was that? So that wasn't algebra, that was just magic. Where'd the 2 go? And for that matter, if this x is 2 and this x is 3, what in the world is this x? I mean, there has to be an answer. And the reason why I know there's an answer is because if I graph 2 to the x and I graph the horizontal line 6, y equals 6, they cross each other. That means there is an answer. So there must be something algebraically going on that's making these base 2's go away, leaving us with x equals 2, making these base 2's go away, leaving us with x equals 3. That means there must be a way to make that base 2 go away so that x is alone. And that is what we're discussing today. And I've already let that cat out of the bag. It's called a logarithm. But everything in math that can be done can be undone. This means that if there is a way to raise constant numbers like 2, 3, 4, 5 to a variable exponent, meaning I have an exponential base underneath an x, then there must be a way to algebraically isolate that exponent. Logarithms, baby. That's what they do. I even printed these notes in color. That's how much I like these things. I thought, darn it, I'm going to make them color in this video. This is what we did last chapter. This is y equals b to the x, the parent exponential function. Well, logarithms are the inverses of exponential functions. They are the inverse operation of raising a constant to an exponent, and we learned way back in the day that inverse functions are just reflections over the line y equals x. There, you see? These are the same graph that is reflected over the line y equals x. This is the parent logarithm. We read it as log base b of x. And if you don't say base b when you talk to me about these things, I'm going to correct you. You need to say it right. Log base b, not log to the b. No, I'll correct you. Not log b, I will correct you. No, it's log base b. And it's specifically of x. I need a super brave volunteer. Super brave volunteer that's going to speak loud enough for the mic to hear you to read this to me. It's not a trick question. Dan, if you're going to do it, make sure you're loud. What does this say? I'm not sure if that was loud enough, but Daniel said square root of 2. Okay, Daniel, speak louder. Read that to me. Is there a 0 in there? Is there a 1 in here? There's nothing written here, right? So this is square root of nothing. Oh. So what does this equal then? Of course it equals nothing. This symbol doesn't have value. It's just a symbol. It performs a job on a number. So on its own, it means nothing. If you ask the calculator square root of and hit enter, it wants to know what you've been drinking. Because square root of what? And it says this thing. What? Square root of what? You see, square root is an operator. It performs a job on something. Log base b is like that. You notice how Daniel had to say of. Square root of. And the question is of what? The symbol does not have value. This is a symbol. It does not have value. It's an operation. And it's waiting for you to tell it what it is performing that operation on. Two things. One, unfortunately in our language, that's a word. And that confuses students. Because it doesn't look like a symbol, it looks like a word. But it's a symbol in mathematics. You see, in China, it's written like that in their textbooks also. Okay? Because it's a symbol, just like that is. Unfortunately, in our language, that's a word. But that's coincidental. Okay? So it's log base b of, and it's waiting for something. It wants to know, what am I performing this operation on? Log base, I don't know, I could say 2. Log base 2 of, and it's going to give me the exact same error. What have you been smoking? Log base 2 of what, bro? Like, I need a number here. So no, you can't divide by log. You can't divide by log base 2. You see, this is a symbol. It doesn't have value. How are you going to divide by plus sign? Okay, it doesn't make any sense. All right? So that's the first thing you need to know. You need to know that it is a symbol. It performs a job on a number. So then the next thing you need to know is, what is that job? This whole box is about inverse operations. We use subtraction to cancel addition, vice versa. They cancel each other in either order. We use multiplication to cancel division. They cancel each other in either order. We use roots to cancel exponents and vice versa. They cancel each other in either order. We use logarithms to cancel exponential bases and vice versa. They cancel each other in either order, and that is bold, baby, as long as the bases match. What does that cancel? What does cube root cancel? Cubes. That's because the indexes match, and that's why it works. Same thing is happening with logarithms. Log base b cancels exponential base b. Exponential base b cancels log base b, as long as the bases match. So here you have that, showing you how that is done. You go, I want that exponential base 2 to go away because I'm trying to isolate my x. So what do we use to cancel exponential base 2? We use log base 2, and it's an operator. It must be performed on both sides, just like every operation you've ever done. If you do it to one side, you do it to the other. So we perform log base 2 of both sides, which is what you see here. Now on the left side, log base 2 and exponential base 2 are inverse operations, and they cancel each other. On the right side, they're not. So they don't cancel each other. And we get that the answer is x equals log base 2 of 6. And you might be thinking, but that didn't tell me anything. I don't know what that equals. I go, yeah, well, you know what? I bet you don't know what this equals either, do you? But you're still willing to write it like that. You see, the square root of 5 is an irrational number. It has no pattern, and it never stops, which means the best way to represent it is with symbols. Specifically, the symbol that wasn't able to do its job. Here, cube root was able to do its job, and that's why the answer is just x with no longer having a cube root sitting around. The cube root is gone because the symbol did its job. The square root is not gone because the square root did not do its job. So we have to say it still. Log base 2 can't do its job on 6. You know why? Because 6 is not a base 2 number. So this is the best way to write that answer. The answer is a little bit bigger than 2.5. I mean, if you wanted to see it, I'll show it to you. There you go. It's that. But it's not very pretty. Now, I hope that everybody understood why the answer had to be between 2 and 3, because 4 is the second power of 2 and 8 is the third power of 2. So hopefully it's very, very obvious that this must be between the second and third power of 2, right? So we knew it was between 2 and 3. Did we know exactly what it was? No. But if you wanted to solve for x algebraically, you would use log base 2 on both sides, and this is what you would get. Now, I do want to bring up something really important, and that's going on from this step to this step. This step to this step. Now, unfortunately, I can't capture this on video, but everybody in the room is going to get to see it happen, okay? So before class started, I took out this bottle of Elmer's glue. I said I needed a bottle. In first period, someone had a water bottle I was able to use, there's one way back there, but that's all in the back of the classroom, so I'm going to leave it back there. So instead, I have this darn near full bottle of Elmer's glue, and here I have a stool, okay? Now, this stool represents exponential base 2. This bottle of glue represents power of x. You see that bottle of glue is currently sitting on this stool, right? Yeah, you see that? Okay. This foot represents log base 2. And log base 2 comes over to exponential base 2 and gets rid of it. Now, I'd like you to tell me where the bottle of glue is. On the floor. You see, it used to be an exponent, and now it's not. It fell down. And the same thing is happening right here in this work. You used to have an exponent, but when the logarithm kicked the base out from underneath of it, it fell down to the floor. So it's important to me that you understand that we didn't end up with 1 to the x. No, it's literally gone. You saw the glue bottle hit the ground. Okay? Okay. I bet you won't forget me kicking that stool. Now, what's happening over here is the same idea, but in reverse. Here, I had a logarithm, and I was trying to solve for x. So since this is log base 3 that I need to go away, I use its inverse operation, exponential base 3, on both sides. What that means is this side of the equation and that side of the equation are now actually exponents above exponential base 3. Why exponential base 3? Because I needed to make sure I matched the log base so they would cancel each other out. Just like I did here. I made the bases match. Now, the exponential base 3 and the log base 3 cancel each other in either order, allowing the x to fall down, leaving us with 3 squared, which is 9. Okay? Yes, Mr. Ram. Fantastic. So I've just kind of got it summed up down here that logarithm is an operation. It does not have value. It is a symbol like a square root bar. And what's really important to me is that you understand what the set of instructions are for a logarithm. I mean, you might not know it, but you all know what the set of instructions for that symbol is. If you could tell me the answer is 3, then you know what its set of instructions are. Its set of instructions are, what number squared gets me a 3? You understand its instructions. You need to understand the instructions of the logarithm. And the logarithm's instructions are, what power of my base gives me my argument? Uh-oh, there's a vocabulary word for you. Argument. This is the argument. In mathematics, the argument is whatever a symbol is acting on. So you could call the inside of a radical the argument. You could call the power above an x an argument. You can call, no, I said that backwards. You could call an x underneath a power, excuse me, an argument. You could call this the argument. When we do trigonometry, whatever the inside of the trigonometry is the argument. So an argument in mathematics is always the inside. Which is where, just using a little bit of review here, your horizontal transformations always occur. Horizontal transformations always occur on the argument of a function. Okay? So we will use that kind of terminology. You will need to use the academic vocabulary. I will need you to say log base b of, and I will need you to call the stuff on the inside the argument when you talk about it. Okay? So what it says is, what power of my base gets me my argument? That's what it says. And to prove a point, right here. What cancels exponential base 2? log base 2. So I asked you before, where'd the 2's go? The answer is they were canceled out. That's algebra. They didn't just go away. How? Why? Where? Algebra, not magic. I'm a mathematician, not a magician. Okay? So if I gave you this, we should be able to know what this equals if we understand the instructions. It says, what power of 2 gets me this 8? What would the answer be? 3. There. The reason why is because 8 is actually a number that could be represented as base 2. But it says, what power of this base gets me this argument? And you might have noticed by now that sometimes I put parentheses around the argument and sometimes I don't, right? That is because the assumption is whatever is immediately written after log base is your argument. And you will notice on a calculator, if you type log, at least the two good, this one and the other good calculator, the solar one, if you type log, it opens a set of parentheses for you because it's saying, here's where the argument begins, and it's waiting for you to tell it where the argument ends. The assumption is whatever is directly after a logarithm is its argument. This is not log base 2 of 4. This is log base 2 of 3 plus 1. That's 1 more than log base 2 of 3. What is log base 2 of 3? I don't know. Some number that's between 1 and 2. It's a little bit bigger than 1 because 2 to the first power is 2. This is log base 2 of 4. So the parentheses matter, which is why I was using them in my exponents in the exponential chapter. They're essentially the same thing. This represents what you get after you raise this to powers. And the question is asking, what powers got me this? Okay. So we have a couple very special logarithms that you have to know, love, breathe, dream about. They're right here. Log base b of 1. It says, what power of b gets me a 1? And I would hope that everybody instantly knows what power always gives you back a 1. The 0 power gives you back a 1. It does not matter what the base of the logarithm is, because everything to the 0 power equals 0, except for 0 to the 0, we don't do that. That's indeterminate. And this one says, what power of b gets me a b? And I hope that everybody instantly knows what power gets you back the same number, the first power. You need to know these two special logarithms very, very well. But I did say it doesn't matter what the base is, but that's kind of not true. I'd like for you to look back at this graph. There were rules about the base of an exponential function. Does anybody remember the two rules? There was 2 rules of the exponential function. Gavin, it's okay, you only know one of them. I can see you trying to raise a hand. He wanted to raise a hand and now he's deer in headlights. No? Jared? It looked like you were about to raise a hand. So you're not wrong, but you kind of tied the rules up into, well, here's what he said. He said at the base is between 0 and 1, it's decreasing. At the base is greater than 1, it's increasing. He's not wrong about that. But he hasn't said, he kind of like danced around the rules with what he just said. There were certain rules about what b could or could not be. Can't be negative, but there's also something else it can't be. 0. And there's one more thing it can't be. One. You see, Jared said between 0 and 1 and then bigger than 1. He specifically avoided negative numbers in the number 0, and he avoided the number 1. And he didn't know why, he didn't remember, and that's okay. The point is, for exponential functions, the base must be positive and cannot be 0. Guess what? For logarithm functions, since they're the same thing, just in a different order, the base must be a positive number, and it cannot be 1. Isn't that nice when it's the exact same rules? Nothing even new to know. Isn't that awesome? Okay. So, let's actually start using our log knowledge on this page here. First thing we're going to do is take these 3 true statements that are written in logarithmic format, and we're going to write them in an equally true statement in an exponential format. What? Well, let me show you what I'm talking about. Can we all agree that me saying that 3 squared equals 9 is equivalent information as saying the square root of 9 is 3? Can we all agree to that? This is a power statement. This is a radical statement. But they tell us the exact same information. It's just in a different format, right? Because I've used inverse operations in the 2 formats. We're going to do that for logarithms. All of these are logarithmic statements. We're going to write them as exponential statements. And here is where you guys become my nice robotic choir. You're all going to reply to me as one, in unison. You're not going to sing. You're just going to reply to me. And here's how this works. When I come across something like this, I might say to my class, okay, class, and by the way, okay, class is your prompt that, oh, he's expecting every one of us to speak back to us, speak back to me now, all 30 of us. He wants to hear all 30 voices, okay? Kind of like when you say, hey, Siri, or hey, Google, or okay. I don't know. I don't talk to any of those things. But my point is, you know, when you greet them, they answer you back. Kind of like how when I say good morning, class, and I am very disappointed when 3 people speak back to me. Could you imagine how mad you'd be if every time you talk to Alexa, it ignored you 5 out of, 83 times? Even 5 out of 83, you'd be pissed, right? I just spoke to you. Answer me back, okay? When I say, okay, class, I'm expecting you all to answer me back in a moment. And here's how the script goes. I would say, okay, class, what cancels log base 3? And as a chorus, I would like to hear 30 voices say exponential base 3. If I say, what cancels log base 5? I'd like to hear as a chorus exponential base 5. Basically, whatever I say, you parrot the inverse operation, and then you say the same base. So if I say, okay, class, what cancels log base b? I'd expect my entire class to say exponential base b. Whatever number I say, you say. I say log, you say exponential. Let's practice, because I want it to come up on the microphone. Okay, class, what cancels log base 3?
Exponential base 3.
I think they heard you. Exponential base 3. That was good. So here's what we're going to do then. We're going to treat the left and right side of this equation as exponents above the base of 3. So now we're saying it's actually 3 to the power of log base 3 of 81. 3 to the power of 4. On the left side, the exponential base 3 and the log base 3 cancel each other out. The glue bottle falls down to the floor and gives you that 81 equals 3 to the 4th. An exponentially true statement. So we didn't solve for anything. We didn't evaluate anything. We just wrote a true statement in another format. It didn't give us any more information. It just wrote it in another format. Okay, class. What cancels log base 5?
Exponential base 5.
Ooh, you guys are a better chorus than first period. Exponential base 5 on both sides then, please. Like that. On the left side, the log base 5 and the exponential base 5 will cancel each other. And it will leave us with this equally true but different format statement that the square root of 5 equals 5 to the 1/2. Now you might think this is ridiculous, but recently a student that graduated 2 years ago texted me, Mr. Thomas Deneen, I don't know if any of you ever knew him or anything. Anyway, TJ texted me. He was my Algebra 2 honors student and my pre-calculus honors student to tell me he was doing logarithms, and he still remembers me saying, okay, class, what cancels log base 10? And everybody replying exponential base 10. And he sent me a picture of the logarithm work that he was working on. By the way, he's at UF. And he had a McCutcheon as a math teacher for 5 years of his life. I'm sure it's not a coincidence. I'm sure there's a correlation there because we're damn good at what we do. Okay, me and my wife. So here, class, What cancels log base 2? Yeah, exponential base 2 on both sides. Then on the left side, exponential base 2 and log base 2 cancel each other and leaves me with this true statement that 1 over 4 is 2 raised to the negative 2. And of course it is, because negative exponents make things move across their own fraction bar. So we haven't done anything except for change the way it looks. No new information, no evaluating, no solving, changing the way it looks using inverse operations. Okay? This is not how other Algebra 2 teachers teach this. This is not how pre-calculus teachers teach this. This is how I teach it, because I remember failing. And I know what made these things look like magic. And I'm not showing you any of the stuff that looked like magic. I'm not showing you any tricks. I'm not showing you any shortcuts. I'm showing you why these things do what they do. Now, if I asked you what cancels log base 2, everybody was quick to say exponential base 2. That's great. So for these, what we're going to be doing is taking the true exponentials and writing them as logarithms. So for these, my script changes a little bit, and I'd say, okay, class. And I would say, what cancels exponential base? The class would reply, log base. You say, if I say log, you say exponential. If I say exponential, you say log, but we both say the same base every time. Cool with that? Let's give it a try. Okay, class. What cancels exponential base 2?
Log base
2. Someone said log base 5, but it is log base 2. It's funny, in first period, one person also said log base 5. Now, for these, I am going to make you write one more line of work. And that's because I'm going to be very picky about you understanding how these things work. And if you don't do this one step that I'm showing you, I'm not going to give you credit on tomorrow's extra credit. It's that important to me. You said log base 2. This is an operation that must be performed on both sides. I want parentheses wrapped around both sides of the equation. We're not solving, we're not evaluating, we're rewriting. On the left side, log base 2 gets to do its job and cancel an exponential base 2. The glue bottle falls down to the floor, and we get 5 equals log base 2 of 32. What I'm not going to allow you to do, just so you know what I'm talking about, is this. If I see you do that, I'm not going to give you credit. Do not do that. The way that that is written, those look like exponents now, but they're not exponents. I was allowing us to be lazy here, because what I should have done was make you rewrite it on the next line. But I'm going to allow you that one laziness, because even I don't ever write that. Sorry, I pointed to the wrong thing. This. Sorry, that sucks. It's not even on the video. I'm going to allow you to skip over writing this side, this line, and just go directly to putting a 3 underneath the left and the right. Like that. Because those are exponents, and they should be in the exponent position. But these will not be exponents, they're arguments. They need to be inside the logarithm. Okay? Now this next one's a little bit tricky because it doesn't look like an exponential statement, but it is. I need to know, I just need someone to tell me, instead of cube root, what exponent is that? 1/3. It's the reciprocal power. So what we really have here is 27 to the 1/3 equals 3. And now we can write it in log format. And I can say, okay, class, what cancels exponential base 27? Log base 27. Great. So you're going to perform log base 27 on both sides of the equation, wrapping the left and the right side inside parentheses. They become your argument. And then on the left, log base 27 can do its job, canceling exponential base 27. The glue bottle falls down. We get 1/3 equals log base 27 of 3. Okay. And the last one is in exponential format, so we can jump straight to how we cancel it. Class, what cancels exponential base 8? Okay, there's less voices. What's going on? I already have people deciding that What I'm doing is not necessary, and they are masters of the material that someone with a math degree failed. I'm telling you, I know the secret, and the secret is constantly repeating yourselves like good little robots. Trust me on that. So what we're going to do is we're going to use log base 8 on both sides of the equation, wrapping both the left and right side of the equation in parentheses so that they represent my argument. On the left side, the exponential base 8 and log base 8 cancel each other out like fire and ice. Glue bottle falls down, exponent is on the ground. 2/3 is what log base 8 of 4 is. Okay. Questions, comments, concerns about, and I hate using this word, converting between logarithmic and exponential form. And the reason why I hate using that word is because this is always the first thing that you learn how to do with logarithms. But most teachers, in fact, every teacher I've ever known, teaches it using tricks and shortcuts and circular logic. And they'll tell you things like, convert this exponential to a logarithmic statement, and you get this. And then they just tell you, like, see, the base is the base, and the exponent and the answer change places. And then you go, but why is log base 2 of 8 3? And then they say, because 2 to the third is 8. But you see, that's just circular logic. If I told you that the thing that I'm sitting at is a table because I could put a plate on it, and then you go, but how do you know you could put a plate on it? And I go, because it's a table. You see how I haven't explained anything. I haven't showed you why this is a truth. I mean, I showed you why square roots do what they do. Because the index matches the power, and they cancel each other. I've showed you why log base 2 of 8 is 3. Because 8 is a base 2 number, and log base 2 gets to do its job canceling the base 2, leaving us with 3. So I don't like to convert. I like to use inverse operations to write it in an equivalent form. Does anybody have any questions about what we've done? No. Okay. I'm telling you, logarithms is not the math to be quiet about when you have a question. Here, I'm about to show you how to do almost all of your extra credit tomorrow. Evaluating logarithms. What do they equal? Look, we're not solving for anything. We are evaluating. Like if I said, what is 2 to the 5th? You're not solving anything. The answer is just 32. That's an evaluation. Each one of these has a numeric value. And our job is to find those numeric values by hand, no technology. And until you are a math blaster, until you are just as good as me, I expect you to do it the way I'm showing you right now. Evaluating using inverse operations. So I just told you log base 2 of 64 has value, a numeric value. You don't know what it is yet. So call that unknown value an x. We are now going to, quote unquote, solve for x. What we're actually doing is solving for our evaluation, but we're going to solve for x using inverse operations. What makes this confusing is that there's a logarithm. I go, fine, let's get rid of it. Class, what cancels log base 2?
Exponential base 2.
Exponential base 2 is exactly what cancels log base 2. So let's use exponential base 2 on both sides, like that. On the left side, those are gone. What I'm left with is 64 equals 2 to the x. And we worked on this kind of math in the last chapter. This is an exponential equation. And you can only solve exponential equations if the bases match. Lucky for us, 64 is a number that is base 2. 64 is 2 to the 6th. And if you write x equals 6 on the next line and don't write what I write on the next line, I will not give you any extra credit on tomorrow's work. This is a step that I must see occurring. I must see you canceling exponential base 2. Class, what cancels exponential base 2? log base 2, I expect to see a log base 2 on both sides of the equation. But why? I know what the answer is. Woo, so do I. Okay? Because I'm trying to teach you how to be successful even when you can't instantly see the answers. Because this process, if these things can be done by hand, always works. And that is algebra. Some of you might have been able to look at it and go, what power of 2 is 64? Oh, 6, that's the answer. Okay, good for you, that's great. But what if you couldn't look at it and tell me what the answer was? Then what would you have done? So instead of having two methods, have one method that always works. This method always works if they can be evaluated by hand. Let's do it again. I'm telling you log base 3 of 1/9 has a numeric value that you can solve for by hand. What you need to do is make the log go away because it's confusing. It's confusing. And I go, class, what cancels log base 3?
Exponential base 3.
Listen to her. She loves logarithms. I love log. Log, log, log. So we're going to use exponential base 3 on both sides of this equation. These bad boys cancel each other, and we are left with 1/9 equals 3 to the x. Now, exponential equations can only be solved by hand and get a numeric value if both sides can be written in the same base. Lucky for us, 9 is a base 3 number. 9's 3 squared. So what is 1/9? 3 to the negative 2. So we have 3 to the negative 2 equals 3 to the x, and I need those pesky 3's to go away, and I say, class, what cancels exponential base 3? And you say?
Log base 3.
Log base 3. I love log. Log, log, log. Okay, so we're going to use log base 3 on both sides of the equation. Wrapping both sides of the equation in parentheses, so the blue stuff becomes my arguments. But I know what the answer is. Yep, so do I. I don't care. There we go. X is negative 2. That means the value of that logarithm was negative 2. And this process that I just showed you works even when they look weird. I think we can all get there, but still it's good notes. What cancels log base 4, class? Exponential base 4 on both sides, please. Like that. They cancel, and you get 8 equals 4 to the x. Of course, we can only solve an exponential equation by hand and get a pretty answer if both sides have a common base. And what is the common base between 8 and 4? It is 2. So this is 2 to the 3rd, and this is 2 to the 2. 2 to the 2x. Because power to power makes me multiply. So this is 2 to the 2 to the x, off to the side. 2 to the 2 to the x is 2 to the 2x. See why it was so important to be good at last chapter? Anyway, at this point is where I would expect you to see, you using log base 2 on both sides. I want to see it. I need to see it. You must show it. Log base 2 of both sides. And then the canceling occurs. But look what you get. You get 2x equals 3. I know I swapped the two sides, but who cares? Because now you get to divide both sides by 2, and you have your final answer. X equals 3/2. And welcome to my nerdy world of logarithms.